I'll be talking about O-minimality and the kind of the classical one, so some finiteness phenomena plus some quantitative stuff. Okay, so for O-minimality, in general, I don't know how many of you have ever seen anything about this theory. It's kind of an attempt to construct a geometry where things are tame, and tame kind of means everything is finite. So there's no, for example, a set cannot have infinitely many connected components. There cannot be infinitely many oscillations. So everything should be as nice as you kind of expect. And I want to start just by giving the definition, because that sounds, I don't know, it's nice to say, but it's not clear how you make sense of this, right? So there's a formalism where you kind of construct a geometry with finiteness properties, and I want to just start by giving the formalism. I promise the talk will not be very formal, but I think just to really appreciate what it means that we're doing time geometry, it's good to at least see the kind of the mathematical framework. So the general framework we're working in is, I start with a notion of a structure. So this is something coming from first order logic or model theory, but I mean, you can think about it very simply as a collection S of sets. So it's going to be a subset of the power set of R, this joint union, the power set of R square, and so on. So it's a collection of subsets of R, subsets of R square, just a big collection. And I mean, these the sets in these collections are called definable sets. They're the definable sets. And those are the sets in our geometry. Okay, so those are the sets that we would like to be nice, finite, whatever. Now, this notion of structure and the terminology definable sets come from first order logic. So basically, what we want is to describe sets that can be defined using logical formulas. So thinking just in terms of the sets, you can say what that means quite simply. But before I give the axioms, I want to also talk about this quantitative aspect. So if you're just talking about classical O-minimality, the structure is what you're dealing with. And then there will be some axioms saying that, okay, this thing should be closed under various logical operations, and these are the axioms. But if you want to make things quantitative, then we should add a little bit more information. Okay, so I'll talk about maybe two kinds of additional information, but let me focus on this, what we call the sharp structures. So when a structure is sharp, it means we want to, for every set in this collection, also associate some complexity parameters. So that eventually we can say things are not just finite, but you can kind of measure how finite they are in terms of some degree or something like that. That's the idea. So the way we do this is we put a filtration on the set. So we are introducing this omega FD, subset of S, where F and D are integers. Okay, so I have a collection of these subsets of S. So each omega FD is just a bunch of sets. And these should be the sets that have some bounded complexity. Okay, so I call F the format and D the degree. And I'll say what it is, but let me first say what this should satisfy. So I want the union over FD of omega FD to be everything. Okay, so every set has some format and complexity. I want this thing to be increasing. So it means I want omega FD to be contained in omega F plus 1D and in omega F D plus 1. Okay, so that's a little quirk of this theory. We're not going to, if you are thinking about, for example, algebraic geometry, then maybe this format would be just dimension, and degree would be the degree of the variety. And every variety has, the dimension, and it has a degree. These are just, it wouldn't really be this increasing filtration. It would be just a partition of the set into things of different degrees. But when you're working with logic, it's not quite as accurate. We cannot associate one degree to a given function. So we are just saying these are all the things that have kind of format up to f and degree up to d. And it makes things a little bit more complicated, but it's kind of unavoidable. It's because what this thing is measuring is how complicated is a logical formula describing a set. Okay, and one set can be described using logical formulas in many ways. Okay, so maybe there's one formula where you're using few variables, so the format is low, but you're using very high degree things. And there's another formula where you're using a lot of formulas, but you're using very small degrees. So this is where this kind of strange filtration comes from. But okay, putting aside this little quirk, I can now define for you what is an O-minimal structure and what is the sharp version. Yes?
Is there saying what you just said in the language of information theory?
Good question. I'm not an expert in information theory, but you can tell me about it later. I do think that, I mean, this kind of thing should be thought of as kind of relating to how much information is encoded in a set. And when I show you the axiom, you'll see that, I mean, it kind of tells you something about how much information can you extract from a set. But how to make this formal, I'm not sure.
Sorry, if you take, say, E8 or something, right, this stuff looks like if you take E8 and you delete a node, everything that's left is kind of finite, right? Any node you delete, all the stuff that remains is finite.
Mm-hmm.
Does that seem like a nice example of this stuff?
So can you repeat the example?
Just imagine the E8 Dinkin diagram, okay?
Yeah.
Vaguely, okay, you don't even need to know what it means. You delete any node,
Mm-hmm.
everything else that remains is finite, and it splits up into nice definable sets.
Well, yeah, I mean, except that, you know, E8 is a diagram. We are really thinking very crudely about subsets of R.
Okay.
Right, so I mean, you know, you take a subset of R, take, I don't know, an interval and take E8, think about the diagram, you know, like fraction of interval, remove one of them, we're still bad. But I'm sure there are like deeper ways of interpreting this. Anyway, so let me just show the axioms. Yes?
The answer is before I came in. Are these properties of the formulas or of the set? So like suppose I have this incredibly complicated formula, which in some very complicated way equals 0. That is a simple thing or?
I mean, so I'm defining a filtration, so a set doesn't really have a single format and degree, right? I'm just saying I have this collection of, this is like all the sets of format.
You understand the point of my question. So suppose I have this very complicated definition, which through some complicated simplification represents a simple thing.
So I'm saying that this would mean that maybe you have a set that belongs to omega fd for some very big f and d, but maybe the same set might also belong to another one, small fd. Yeah, but you cannot really minimize because, I mean, you could say, let's just take the minimal one. Yeah. But because I have two parameters, it's not clear with which order you should minimize. So that's why you really should keep track of these two different things. Okay, I like all these questions. It's good. So, okay, so now let me state some axioms and I'll kind of tell you at the same time what is an O-minimal structure and what is this quantitative version. I just want to mention that, okay, I'm talking mostly about this sharp case. There's another version where if you want to be a bit less, less ambitious, you could just say, let's associate a format. Forget about the degree. And I mean, I'll show you kind of when you have format and degree, we require polynomial dependence on D, and then we get some sharper estimates. But if you just want to know, can I make everything quantitative? Then I could have used just a single parameter. And I mean, sometimes we are able to construct these kinds of structure where you have one parameter and everything is like effectively controlled in terms of the parameter, but we can't get this kind of sharper control. Okay, so this is where this word sharp comes from. And I mean, you could also introduce a similar thing where you had a single parameter and you don't care about the polynomial dependence on degree. So I'll say a little bit about this, but I'll focus mostly on this sharp version. Okay, so with this said, let's go to the axioms. So my axioms. Okay, so first of all, suppose I have A and B subsets of some Rn. And okay, so let me do side by side. So in the O-minimal case, I'll just say, so suppose that A and B are definable sets. Okay, so this is my assumption, but in the sharp side, I'll say, suppose A and B are actually, or yeah, let me say that A is in omega F dA, and B is in omega F dB. Okay, so I'm going to take a pair of sets, and now I'll state some closure axioms. So then we should be closed under various things. So for example, A union B, A intersect B, I don't know, are in set minus A. So, okay, so let's say this should be in S, this should be in S, and pi n minus 1. So this is projection to the first n minus 1 coordinates of A should be in S, and R times A and A times R should be in S. Okay, so these are the kind of closure axioms of a structure. So structure should be closed under Boolean operations like union, intersection, complement. It should be closed under projections. So this is a projection to the first n minus 1 coordinate, but you can repeat this several times. And it should be closed under taking Cartesian products. Okay, so these are the axioms of a structure. Now, if you kind of want to pass to this more sharp side, then instead you would say that A union B and A intersect B should be in omega F dA plus dB. Okay, so we are saying unions and intersections, you keep the format, but you sum up the degrees. This complement, it's the same thing, so let me just write here. So the same thing now would be in omega F dA. Okay, so complements don't change the format and the degree. The projection also does not change format and degree. And this guy, it increases the format by 1 because it kind of increased the number of variables. Okay, so we are basically imposing the same closure axioms, but we're just keeping track of how these complexity parameters vary when you use all these closure things. Okay, so you'll notice that the format really only increases when we increase the number of variables. So, I mean, the ambient space. So that's why the format is kind of like the ambient dimension, but we are not claiming that it drops when you take a projection. Right, so if here, when I did phi minus 1, I wrote F minus 1, then the format would really be just precisely the ambient dimension, but I'm not asserting this. So it's kind of remembering, if you wrote a formula, how many variables were used in your formula. Maybe you used some variables and then you used quantifiers to get rid of them, but this format remembers how many variables you used. Okay, so this is roughly the meaning of format. And okay, degree kind of records, I don't know, just the complexity of how many unions you took, how many intersections you took, that kind of thing. Okay, but so all of these axioms are the axioms of what is called a structure, a first order structure, and this would be a sharp first order structure, and it's not O-minimality yet. It has nothing to do with O-minimality. So O-minimality is about structures that extend the real field. So you are allowed to define addition and multiplication there and the order relation. And so you need to add something to these axioms. Like these axioms I could use for any first order logical theory. So I need kind of a couple more axioms. So the first of them is about the real field. So I want to say that if I have a polynomial P now in n variables, then, okay, in the O-minimal case, I'll just say P is equal to 0 is definable. Okay, so a structure extends the real field if every polynomial is defined. So it means in particular you can define addition, multiplication, and by projection you can also get the order relation. So you can say x is bigger than y if x minus y is equal to z squared for some z. Okay, so I mean somehow putting this in allows you to define everything that you can define with a field and its order. And again, in the sharp case, we'll make the same, okay, it still should be contained, but now we will say what is the format and the degree. And the format and the degree is exactly what you expect. It's omega n and the degree of p. Okay, so it means that this filtration that we've introduced, it kind of extends, it agrees with the usual notion if we are restricting to just algebraic things. So we're trying to take like the dimension and degree that we have in the algebraic category and somehow extend it now to a larger structure. Okay, so this is what logicians would call like a structure over the real field. And this is the sharp variant. It's still not O-minimal. Okay, I said O-minimality should say something about finiteness, about, you know, all sets being nice. And I didn't say anything. I could have taken S to be just, I could have taken every subsets of Rn to be in my S, and still it would be closed under everything I said. Right, so it wouldn't really work out that way. We should say something that makes things finite. And that's the final axiom, and that is what is called O-minimality. O-minimality, now it's O-minimality. In O-minimality, we take now a set X, which is a subset of R, and we are, okay, and it's in S. Okay, so we take a definable set, which is a subset of R, and then the axiom says that X is a finite union of points and intervals. Okay, so in order for the structure to be O-minimal, you are just imposing something on the one-dimensional, I mean, subsets of R. You're saying when I have subsets of R, I want them to be tame. It's very easy to understand what it means for a subset of R to be tame. Okay, because I mean, when we have subset of R, I said, you know, tame sets should have finitely many connected components, for example. But if you're in R, then having finitely many connected components really forces you to be just a union of finitely many points and intervals. Okay, so we have a very kind of simple definition for what we want in the case of subsets of R. And the claim is that if you have all these other axioms, this is actually enough to impose finiteness on all the sets. So now take a subset of R2. Okay, maybe this axiom doesn't say anything about it, but the claim is that somehow if you have a structure that's closed under all of these things, then every subset of R2 will also have finitely many connected components. Because if not, you could somehow cook up a subset of R that would have infinitely many connected components. So that's the idea of O-minimality, and it works. And I will show some theorems, I mean, to the effect that indeed imposing this axiom means that all the sets in every dimension are very nicely behaved. And now this axiom you want to replace by kind of a sharper version. Yes?
Sorry, maybe you said this, but does it matter when the intervals are open or closed?
The intervals could be either, I mean, whatever you like. You could take them open and then take the endpoints to be as extra, because I said a finite union of.
Yeah, so you just take.
Yeah, so you can take them, but they could be like infinite intervals. So they could be like half infinite intervals. So just any collection of intervals, finite collection. So in sharp O-minimality, I'm just going to impose that the number of points or intervals. Oh, okay, so let me say that now X is not just in S, it's in a certain piece of my filtration, it's in omega FD. Then I want the number of points to be less than some polynomial depending on the format of the degree. Okay, where these guys, I have some sequence of polynomials, P sub F. This is a polynomial, let's say with integer coefficients in the variable D. I have this sequence. And this is part of the data that defines my structure, okay? So when I have a sharply O-minimal structure, it means that whenever you end up with a subset of R, if you know what is the format, then you know that the number of points and intervals grows polynomially in the degree. Okay, and which polynomial it is, it depends on the structure. So there is this sequence for every format I have a polynomial. Maybe it could be, if you're thinking about something like algebraic geometry, you might think it should be something like d to the power f. Right? By Bezout theory, if I intersected equations in in n variables, and they're all of degree d, then I expect something like d to the n solutions, right? So maybe you should think that this polynomial should be something like d to the n, but maybe in a more complicated structure, this thing might be d to the power 2 to the 2 to the f. Right, so I don't care how it depends on f. I'm not making any assertions about how things depend on f. And I should say that in practice, the dependence on f, even in simple cases, is quite bad. So this is a phenomenon known even from the semi-algebraic geometry. Even if you're doing only algebraic things, and you're trying to do like effective semi-algebraic geometry, you can usually expect good bounds in terms of the degrees of your equation, but you cannot expect something very good in terms of the number of variables. So I mean, the best known bounds usually are at least doubly exponential in the number of variables. So you can expect these polynomials to look something like d to the power 2 to the f. I mean, I'm not claiming this is actually even correct, but at least something like d to the power 2 to the f. So the idea is we are really going to be thinking about a fixed format usually, and we're going to be playing with the degree and seeing how things grow with the degree. And this is this point where I said that's why it's called sharp, because it gives you some sharp control in terms of the degree. If you don't really care about this aspect, if in your problem you want to make things quantitative, you want to know that I can estimate everything, and you don't really care about polynomial control in terms of the degree parameter, then we could have forgotten about this, and I could have just said, well, this would be some explicit function of f. Like forget about the degree. Suppose you make all the same definitions, but just say I want to have some functions here of f that I am able to compute. And this will give me a kind of a quantitative version of O-minimality, but not what we call sharp. And we have some structures that I will mention where we know how to make it quantitative, but we don't know how to make it sharp. We don't know how to get this really polynomial control on degrees. The reason I'm focusing on this version is that, well, first of all, conjecturally, I think it should contain a lot of interesting things that are maybe of interest to physicists. But also, when we have this polynomial control, we can prove stronger theorems. Okay, so there are some theorems that I will mention where you really need this type of polynomial growth. And I think in terms of measuring information, this is also interesting because these types of theorems will tell you something as follows. Let's say I have a set definable in this sharp structure, and I want to, let's say, approximate it. I want to understand how much information is in the set. So I'm going to try to write an algebraic approximation for my set. I have a complicated curve. I would like to find an algebraic curve that approximates it well. So if you have this kind of thing, then I will be able to say, well, the degree of the algebraic curve that you need is like a polynomial in log epsilon, where epsilon is the error that you allow. Okay, and if I don't make this polynomial assumption, I will not be able to prove such a thing. Okay, so if you want to get results where you're measuring the number of bits, and they should be like something like a polynomial in the log of the size of the error, then this kind of polynomial dependence becomes really important. And if you just are trying to say, well, I defined some sets and I have a specific set I'm interested in, I define it and I would like to know that I can compute a bound, then maybe this polynomial dependence is not so important. Okay, so just keep it in mind depending on what your intended goal is. Yeah.
So I noticed in algebraic geometry, we want to say that A intersection B has degree dA times dB, right? Why
Yeah,
do you
good question.
Yeah.
Yeah, many people often ask me that. So, you could have said the multiple here. You see, because I really only say that I have a sequence PF, then it doesn't really matter because eventually I can take these polynomials to be something like d to the power n, right? And then even if you took the sum of the degrees, so I'm saying, suppose you had two equations in two variables, then you intersect. I'm going to say, well, it's still degree d, not d squared, but it's format 2, not format 1. And then I'll say that pf, I'll say that p2 is equal to d squared. Right? And then if you took two equations of degree d, you intersected them, you get a set of points of degree d, but format 2. And then the number of points is going to be bounded by p2 of t, which is d squared. So it's really just a question of how you index these polynomials. But I agree that alternatively, one might have taken the product here. But it somehow doesn't matter, just amounts to changing these polynomials. Other questions? Okay, so let me make some theorems about this. Say why it's useful. So the type of theorem that we usually want to prove is, okay, we've made some assumptions about subsets of the real line, right? That's this O-minimality assumption, or we made a stronger assumption with the sharp case. And then we would like to prove something about all sets. Okay, so the kinds of things that we can say so let's do an example of a theorem. So suppose I have a set A which is now definable, or in the other case it would be definable with a given format and degree, then A admits finite triangulation. I mean, it's homeomorphic to a simplicial complex with finitely many pieces. So that already means that it has finitely many connected components, and also it has finite homology groups, and you can get a lot of finiteness of topological things just by knowing that you have a finite triangulation. And then, so here you want to say that, okay, I have a finite triangulation and I know something about it. And what can I know is that the number of simplisets is less than or equal to some polynomial depending on the format in the degrees. Okay, so now that if you have this structure and you know that on the level of subset of R it behaves well, then actually this kind of theorem, finiteness theorem that we knew classically from O-minimality, we can extend it to a stronger theorem where you get control. Okay, and I mean, proving this basically amounts to following the proof of this. And in the proof of this, it's a proof from O-minimality. So you just use the axioms, and at some point you will be using finiteness that comes from the real line. And whenever you use that, you can now have some explicit control. And if you just follow the steps, you'll see that you will now get a polynomial bound for the size of the triangulation. Okay, so that's the idea, and that's kind of how it usually works. So the idea is you can take proofs from O-minimality. In some sense, the only thing that these proofs could be using is they are using these axioms, and eventually they deduce finiteness from the real line. And then you just kind of repeat it, but whenever you deduce finiteness, you get some bounds, and hopefully you will get kind of a good sharp estimate if you are in a sharp O-minimal structure. Okay, so let me give some examples, because so far I've just defined things and I've said nothing about do these things even exist. So the most classical example is the structure denoted by R-alg. So this is what is called semi-algebraic geometry. Semi-algebraic geometry. Okay, so that's the smallest one. That basically means I'm only putting in the things that I have to according to this axis. Okay, so I have to put the polynomials, I mean zero loci of polynomials, that was one of my axioms, and then I have to close by everything. So what I get is basically every set that you can define using formulas just involving polynomials and addition, multiplication, and logical quantifiers. And this is called semi-algebraic sets, and I mean the collection of all of them is called semi-algebraic geometry, and this is an O-minimal structure. Okay, so this is O-minimal, and it's even sharply O-minimal. So here you can introduce some filtration, and this, okay, of course, they didn't use this terminology, but it basically goes back to classical proofs by Tarski, Zeidenberg, maybe Tom. So I mean, people who studied semi-algebraic geometry, they showed how to do things effectively, how you can eliminate quantifiers effectively. And if you follow their proofs carefully, you can even get that, I mean, they were producing this kind of sharp example. Yes?
Is there a reason to do or not to do something parallel over C or another field?
I mean, it's a very interesting question. Talk after me, Ben Isaac will talk about cell decompositions. I'll get to cell decomposition. That's kind of the main technical tool here. And he will talk about some complex version of this. So there are many works, like Raf Klackers has a lot of, who is also here. He has a lot of work on doing some analogs of O-minimality in valued fields, so in p-adics. And so some things are similar, some things are different. It's definitely a very interesting topic. Yeah, so okay, this one is O-minimal, but maybe it's not that surprising. I mean, you only took algebraic operations, then you only get finite things. I mean, it's also a deep result, but it's perhaps to be expected. the next example, which is still classical and predates O-minimality, is what is called Rn. And these are also called the globally subanalytic. These are the globally subanalytic sets. And this is what you get when you start with R-alt, you start with semi-algebraic geometry, and then you add to it the graphs of all restricted analytic functions. Okay, so I'm going to add every function f, let's say from 0, 1 to the n into R, which is analytic. So when I say analytic on a complex, on a closed set, I mean it's analytic in a neighborhood of the set. Okay, so we are going to put into our structure all the functions that are analytic in some compact set, like 0, 1 to the n, and then we are going to close under all the axioms. Okay, so maybe it's easy to think about it in logical terms. In logical terms, it means now you can define anything that can be defined by formulas involving addition, multiplication, polynomials, but now also every analytic function. But if you just restrict it to some compact domain where it's analytic. Okay, so what I don't put here is something like sin x. Okay, sin x is analytic on all of R, but I'm requiring it to be analytic on some compact set. It's a good thing I'm imposing this restriction, because if you did add sine, you definitely get something that's not O-minimal. Okay, if you put the sine function into your structure, you can then intersect, you can say take y is equal to sine x, intersect with y is equal to 0, and we'll get an infinite collection of x's, right? So I don't get an O-minimal structure. But the claim is that you kind of cannot hide oscillation. I mean, this oscillation comes from having a non-compact set. If you are using compact sets and analytic functions, you cannot hide any oscillations. Whatever you write using formulas like this will always be finite. Okay, so this is, again, it predates O-minimality, but I would say kind of it's, so okay, here I forgot to say this is basically Tarski-Seidenberg. And this I would attribute essentially to Gabrielov, and maybe then Van den Dries kind of formulated this in the language of O-minimality. But Gabrielov, I mean, before O-minimality was introduced, he proved the theorem about these globally analytic sets. He proved that a complement of a projection of a globally analytic set is again a complement of a projection. That's called the complement theorem, and that actually implies O-minimality in this case rather easily. Okay, so kind of it was known that this structure is globally subanalytic, is O-minimal before people even invented O-minimal. So this, I didn't say anything. So this structure is O-minimal, is my claim. But it's not sharply O-minimal. Okay, so it's O-minimal, and that's what Gabrielov essentially showed. It's not sharply O-minimal. Well, first of all, it's not very surprising because, I mean, it's not clear how you would measure the complexity of just an arbitrary analytic function. But I mean, I'm making a formal claim. I'm saying that you cannot put any filtration on this structure in such a way that it would become sharply O-minimal. Okay, so maybe this is an exercise for you. I don't want to go into too many details, but the idea is that you take a very lacunary series. Consider something like f of z is equal to, sum of z to the an, and take this an to be, very fast growing, going very fast to infinity. And if you do it like this, you can see that, I mean, a function like that cannot belong to any sharply O-minimal structure, but an exercise. It's a good exercise in going through the definition. Okay, so I said there is this example, which is sharply O-minimal, but for a kind of a simple reason, and there is this next example, which is not sharply O-minimal. Okay, so are there other examples that are sharply O-minimal? First, let me introduce one more O-minimal structure that's kind of important in many of the applications, especially to Hodge theory, that I guess could be of interest to physicists. So that's the structure R and X. So this is basically where you took Rn that I just defined above, and we also add the exponential function. Okay, so I'm adding e to the x as a function from R to R. Okay, so this is a structure that's again O-minimal. And it wasn't, I mean, the first thing to note is that this e to the x was not in the previous structure because it's an analytic function, but it's not restricted. I'm taking it on all of R. Okay, so it was not belonging here, at least not by definition. I mean, maybe you might think that I can somehow cook up this e to the x using restricted functions and some logical formulas, but in fact you cannot. Okay, so when you add e to the x, you really get a different structure, a bigger structure, and then it's a fact that it's again O-minimal, and of course it's not sharply O-minimal. Okay, even if you didn't add x, it's not sharply O-minimal, and certainly after you add e to the x, it just gets bigger, and it cannot be sharply O-minimal. So the O-minimality of this structure is quite important. It's what's used in many applications to Hodge theory. Okay, and it's not sharply. Right? Any questions so far?
I have kind of a naive question.
Yeah.
Why is x not a good function from the interval from O to 1 to R? Like it is I can write the power series, sum it, it's convergent everywhere.
Say again? What?
Why is the exponential function not a good function from the interval from 0 to 1 to R?
No, for the interval, it is defined. So if you restrict it to any finite interval, it's actually already in R sub n. But I mean, here I added e to the x not on the interval. I added e to the x on the whole real line.
Yeah, I guess maybe I'm confused, but what it means to have a function in R analytic that's only defined in a finite.
Okay, sorry. So what I mean by this is when I add I mean, my structures are always just collections of sets. Right, so when
So it's the set of, it's the intersection of the analytic function, the
mean,
zeros of the analytic function.
I'm basically taking the graph, but only over that point.
Great.
Or if you like, you can think that, well, I define the function to be 0 outside of the, so I'm taking different ways of doing it. Maybe logicians, they like to have the function always defined, so that the formula makes sense. So they'll just say, okay, I define it on the interval to be whatever the function is, and outside of the interval, I'll just define it to be identical 0. That's another way of doing it. But yeah, thank you, it's a good point. Okay, so I want to get to some versions of this or something where you can have this sharpness. Otherwise, I've given you no examples, essentially, except the algebraic one. And for that, I need to digress a little bit on a theory of Chovansky. So Chovansky, so he has kind of two definitions of Pfaffian or Noetherian functions. So he defined both of these together, I guess, around I don't know, late 70s. Maybe Dmitry knows better than me. When did Chovansky do this? Late 70s? Early 80s? 80s. Yeah, doesn't matter. Okay, around then, around 1980. So the idea was to somehow define there was no notion of this sharp O-minimality then, but the idea was to introduce some functions where you can hope to control things more explicitly than in just O-minimality. So you want functions where you can give really bounds on the number of zeros of solutions in terms of some data that defines the function. And the data is going to be differential equations in both of Chovansky's definitions. In fact, in every example that I know, where we can do effective things, we are adding actually functions that are satisfying some differential equation. You might ask about solutions of functional equations, or you might ask about the Riemann zeta function. I don't know. I mean, you could put any function into this framework, at least if you restrict it, say, to a compact interval, then the Riemann zeta function restricted to a compact interval, it would be in an O-minima structure. Can you make some effective estimates? Then I have no idea in any case where you don't have differential equations. Okay, but let's go to Chovansky's definition, which I will simplify a little bit for the presentation. So I'm going to fix a domain which I just take to be a product of intervals. So, and I'll take these to be, okay. There's two versions of this theory. So when this ij is finite, then this will be called restricted. Will be the restricted case. Okay, so just as before, when I was doing analytic functions, I said if I'm restricting them to some compact intervals, then it's restricted analytic function. And now we want to kind of define functions on this G that are transcendental, so they're not already in RH, but where we can still control things about the zeros. So yeah, then we'll call a sequence of functions f1 up to fl from G into R. We'll call them Noetherian. Or yeah, I mean, Noetherian chain even. So it's like a chain of functions, so it's called the Noetherian chain. If you have any system of algebraic differential equations for them. Okay, so I want dfi by dxj to be equal to some polynomial combination of, okay, let's say x1 up to xn and my function f1 up to fl. Okay, so that's a very general notion of, it's just functions that satisfy any system of nonlinear differential equations. So this is called Noetherian, and we know less about them. And then there's another definition that Chovansky made. I mean, I think he was basically trying to first say something about these, but it's very difficult to say something about this. And then he realized that if you make a certain simplifying assumption, he could prove a very strong theorem. So the simplifying assumption, so I said this is called a Noetherian chain in this case, and it's called a Pfaffian. If I make a triangularity assumption. So if Pij is actually a polynomial in the x's and only f1 up to fj. Okay, so I'm not allowing this kind of non-triangular system. So now it really looks like a chain where the first function, it satisfies a derivative. I mean, the derivative of the first function is just a polynomial in the first function, in the variable. Then the second one, the derivatives can depend on the second function and the first function, and so on. So you have this kind of triangular chain structure. And it turns out that if you make this assumption, then you can prove much more about the complexity of the zero loci of these functions. Okay, and okay, let me kind of summarize the whole theorem. So maybe I'll go there. Any question about these definitions of Pfaffian and Noetherian functions? Yeah, so let me state a theorem about the restricted Pfaffian function. So this is a theorem that is a combination of the work of Chovansky and then Gabrielov. Vorobyov, and me. But these are many different people. So this is something that Chovansky did in the 80s. Then Gabrielov worked on it a lot in the 90s. He worked with Vorobyov on it in the, 2000s. And then finally, Vorobyov and I had a paper maybe a few years ago. So I'm just formulating it all at once. Basically says that the structure R Pfaff, so that's the restricted Pfaffian. You put all the restricted Pfaffian functions into your structure is this sharply O-minimal. Okay, so there is actually a filtration where you can put all of the solutions of any of these functions into your structure, and it will be sharply O-minimal with the definition I gave before. Okay, and I mean, this restriction, I believe it's not essential. It's, yeah, there's an ongoing work which is delayed completely due to my laziness, but I believe one can do it for Pfaffian as well. So this was the theorem. And let me say a little bit what is the format and degree. So I'm saying you can somehow introduce here filtration with a format and degree. The idea is basically that, you know, we are measuring the complexity of these differential equations. Okay, so when you define a Pfaffian function, you had to give a chain like this, and you have to give a bunch of polynomials, I mean, the kind of the things that show up in your differential equations. And if you measure the number of variables in the chain, that would be like the format of a function. If you measure all the degrees of the polynomial, that would be the degree of the function. And then, okay, you put these functions into your structure, and now you close under all the axioms, and you get some filtration. And this is roughly the filtration with respect to which things are sharply or minimal, although it's a bit more complicated than that. So it's not quite so direct to construct the sharply or minimal filtration here, but I don't want to get bogged down into technical details. You can, even without knowing the construction, just knowing the axiomatics, you know that I have a filtration and it contains all the restricted Pfaffian functions, and you know, you're good to go. Any questions about that? Okay, so I mentioned Pfaffian and Noetherian. I want to say something about Noetherian. So there was a kind of a conjecture by Gabrielov, by Chovansky, sorry. So, and then later in some different, more local form by Gabrielov and Chovansky. Roughly to the effect that if you take the structure and you put the restricted Noetherian functions, this is effective. Okay, so I'm not saying sharp. They were not quite as ambitious as sharp, but I mean, effective, again, I didn't formally define, but basically I mean the same thing, but without this polynomial dependence on degrees. So basically what Chovansky said was, when you have solutions of a Noetherian system of equations, but now restricted to a compact domain, you should be able to compute everything about the complexity of these functions just using this data that define the function. And so we should be able to have some, let's say you intersect a certain number of Noetherian functions, there should be something like a Bezout theorem that tells you how many points of intersections you have. Okay, and I mean later Gabrielov and Chovansky, they had I mean, Chovansky, it was kind of a folklore conjecture that was mentioned in his ICM talk about Pfaffian functions, and then Gabrielov and Chovansky made it a bit more precise a bit later in the late 90s in a kind of a more local version. But anyway, this was the conjecture, and what I don't know that it's sharply or minimal, but I do know we now do have the theorem that this structure is effective. So this conjecture is settled, and to settle it, actually, you have to pass to a slightly bigger structure. So this Noetherian structure, this restricted Noetherian function, is contained in something I call the structure of log Noetherian functions, and I'll just briefly tell you what they are. So the log Noetherian functions, it's basically you take this system of equations, but you allow logarithmic singularities. So in order to be log Noetherian, it basically means that you add xj here. Okay, so we are taking solutions of a system of equations, but we are allowing a logarithmic singularity. So instead of deriving by d by dx, we're deriving by x d by dx. So that's like doing a log derivative. And I still want the functions to be analytic. Okay, so it's not that I'm allowing singular functions. I'm just allowing more complicated systems of equations. And this turns out to make a big difference. Like when you try to work with these functions, these log Noetherian functions are much better behaved. And then I was able to prove that, so the theorem is that this RLN is effective, and even if you add exp, is effectively O-minimal. So you can kind of bound everything about sets defined in this structure using the data. And again, the data, I mean, the format and degree is basically you count the number of functions you have here in the chain and the degrees of this polynomial. Okay, so the reason I'm mentioning this is that, okay, so now we have two examples. This is the main example of a sharply O-minimal thing, and this is the main example of, I don't know, an effectively O-minimal one, where we don't know if it's sharp. I do conjecture that it's sharp, so the conjecture is that this R, L, N, X is sharply O-minimal. And I think that, I mean, so if in physics it's useful to have this kind of quantitative version of finiteness, then these are kind of two structures to keep in mind. So, okay, when the functions are Pfaffian, then we can really say a lot. When the functions are Noetherian or these log Noetherian functions, then we can say something, but not with this sharp polynomial control. Okay, so let me tell you a little bit about what kind of functions are in these structures, functions you might know, you might like from your physical endeavors.
To assume restrictedness in the document theory?
Yeah, sorry. So I dropped this out, but yeah, this in the Noetherian case, it really has to be restricted to have any chance of working. Like you see this when you allow triangular systems, when you enforce triangular systems, then you rule out certain things, and that's why the Pfaffian case you can have even unrestricted. But when you do a system that's not triangular, you could write like sine and cosine. They're solutions of a system, right? I could write that sine prime is cosine, cosine prime is, and then I would, if I allow unrestricted solutions of Noetherian systems, definitely I don't get O-minimality. Not sharp, but I mean I don't get O-minimality at all, right? So you do have to impose that it's on a compact domain. Yes.
What's the format here? Is it complicated to state, or is it
What's the
format?
The format. So I mean, initially, it's you took some basic functions. You can think that, well, the format is the number of variables and functions in the chain, and the degree is like I don't know, the maximum of all the degrees in the chain. But that's, then you have to modify it, I mean, to really get a good filtration. So there is a filtration where every function has this format and degree, but then what is the whole filtration? You have to, it's much more complicated to describe. But I mean, somehow when you are using the O-minimality, it's enough to know. So let's say you have a formula and you want to know, can I effectively bound something? Then it's enough for me to know that all the basic functions in the formula are of a given format and degree. So I'm saying you can assume that a Noetherian function, the format is at most the number of variables in this chain, and the degree is at most all the degrees in the differential equations.
But how does that relate to this problem about sine, for example, right? Because we need the format of sine to grow as we.
Right. Sorry. So you can either normalize things to, let's say, to always lie on the unit ball, or if not, then you should take maximum. So now the format will also depend on, let's say, the size of the ball that you're restricted to and the maximum of all the functions. Thank you. That's a very good point. Yeah, I forgot about that. So yeah, here we should take the format also depending on the size of we're restricting to a compact thing, and as it grows larger, our bounds will get worse and worse. So the format has to also record the size of the balls and the maxima of all the functions and that kind of stuff. Yeah. So a few examples. So if you have, for example, e to the x, that's a Pfaffian function. That's the prime example, right? It's just the derivative of e to the x is e to the x. So it satisfies a very simple triangular system. It's also the case that elliptic functions and abelian functions, they are all in kind of this Pfaff. Okay, and if you these should be restricted to their fundamental domain. Okay, so e to the x, you can even take it unrestricted and it's Pfaffian. These guys, of course, they are periodic. So if you don't restrict them, they would never be O-minimal. But if you restrict them to the fundamental domain, you can actually show that they satisfy these Pfaffian systems. Okay, so any kind of geometry that you want to do with elliptic curves, abelian varieties, one could also put Abel-Jacobi maps here if you want to, look at general genus G curves. So Abel-Jacobi maps, maybe I'll add, if you know what they are. They are all Pfaffian. Now, what isn't Pfaffian and why, or what isn't Pfaffian as far as we know, and why was Chovansky interested in Noetherian? Period integrals apparently are not Pfaffian. I mean, as far as we know, are not Pfaffian in general. Even though they do satisfy systems of differential equations. Okay, so if you take any family of abelian varieties, take any algebraic form, and you integrate over a cycle in homology, you do get differential equations for this. These are called Gauss-Manning connections, and I'm sure we'll hear a lot about them in the talks on Hodge theory. So you have differential equations, but it's just that they don't have this triangular structure. These are linear systems of differential equations, but without any, I mean, the matrix doesn't need to be upper triangular. So you're not going to get this Pfaffian property for the functions. And I mean, the question that maybe Chovansky was interested in, and maybe part of the reason he developed even the theory of Pfaffian functions, is to try to understand things about period integrals. Okay, so for example, let's say you take just you take an integral like I of t, which is, I'm going to write an integral over gamma t, a cycle inside an algebraic curve. Let's say I just of some omega, where h is, let's say, a Hamiltonian in two variables. I'm going to fix Hamiltonian in two variables. And I'm looking at the level curve, so I'm looking at h is equal to t. Now I'm integrating a form. Okay, so I'll have, the level curves of the Hamiltonian might look something like this. And now I'm using the Hamiltonian as my parameter t, so the value here would be t, and for every t I integrate my form along some cycle living in this level curve h is equal to t. So this is the kind of functions that you wanted to understand. It's related to the Hilbert 16th problem, where you're doing perturbations of Hamiltonian systems, and he wanted to understand, can you give a bound, for example, for these functions? And if the system were triangular, then you could use his theory of Pfaffian functions, but it is not. So the system is some linear system which is not triangular, so it is actually Noetherian. Now I should say that it's really Noetherian around a smooth point like this. Okay, it's not, I mean, this linear system that we have, it's a singular system. So this period integrals, they would not be solutions of a nice differential equation like in the Noetherian case. But the claim is that these period integrals, they are not Pfaffian in general, but they are always in this RLNX structure. Okay, so the singularities of these systems that you get, these Gauss-Manning connections, they are what are called flat connections with regular singularities. And if you put them in the correct model, it means exactly that you will have only these log type singularities. Okay, so the system that you write, it will, I had equations here on the board where I allowed, x times d by dx. And if you allow these kinds of systems, you will always get all of your period integrals in this structure. Okay, so in this structure, you can basically study all of the period integrals, not just in one variable like this, but in any number of variables. Okay, so I think for this reason, maybe for the applications that are related to Hodge theory and physics, this structure might be more suitable than the Pfaffian structure. On the other hand, we know less about it. So, yes.
So this would be true for the period integrals of Calabi manifold, for instance.
Yeah, any system of, if you take any family of algebraic varieties, any one form, any family of homology, then it will satisfy. If it satisfies Gauss-Manning, then it's in this structure. Well, I mean, it should satisfy. Yeah, for Gauss-Manning, for sure, it's true. If you have just a connection, it should be a connection with, a flat connection with regular singular growth and quasi-unipotent monodromy. So, I mean, if the connection does not have quasi-unipotent monodromy, then the solutions are going to look like, like t to the lambda where lambda is not a real number, and then this is never going to be O-minimal, right? This involves oscillation. So you need this assumption about the monodromy of the connection to be quasi-unipotent, or at least to have spectrum on the unit circle. But I mean, up to that, they are always in the structure. But I should also mention that this structure, I mean, this is kind of using only a very limited part of this structure because these are all linear systems of equations. Okay, and this structure contains any solution of any nonlinear equation. You can put, you know, geodesics of your favorite, I don't know, Riemannian matrix or whatever you can describe with differential equations that are completely integrable. You should know how to derivate with each of the variables. But if you have that, then even nonlinear systems you can get in this structure. Yes.
Are there statements about PDEs, you know, like things that would come up in physics?
So, I mean, it is kind of a system of PDEs when I define, because I said, but it's an overdetermined PDE. It's a PDE where you really know how to derive in every direction. Right, so I said that so it's kind of like a completely integrable system, if you like. I mean, doing something similar for PDEs without complete integrability, it would be very interesting, but I think way out of reach. I mean, it's even for very simple cases. Let's say you have a flow box. So you're just imposing. Let's say I have a vector field, and I'm looking at its flow from. I have a vector field, even a polynomial vector field, right? So you know, P d by dx plus Q d by dy, and I'm looking at the flow. And I'm taking the function mapping from here to here. So just the time one flow, or the flow from x is equal to 0, x is equal to 1. Suppose there are no singularities. Everything is naturally defined here. So understanding this map is extremely difficult, I would say. I mean, it's related to the Hilbert-16 problem, and we don't know anything like effectivity, and I think it would be like amazing if one could get something for this kind of use. So this is what you get when you impose just a single vector field, and you impose some initial conditions here, and you try to see how the solutions behave here. So that's a very, very deep problem, I think.
But is this sort of the goal? I mean, is the idea to push this further in this direction?
Well, I mean, depends on how ambitious you want to be. I think, it should be also effectively or minimal, sharply or minimal. You can always make these conjectures, but I have no idea how to even approach it. I mean, when you have completely integrable systems, something like this, then okay, we have some control, we get effectivity, and one can try to push and get this better control, like polynomial control. If you have just PDEs, then okay, it requires new ideas, and I would say a real breakthrough in order to approach something like this. Yeah, I thought a lot even about just this polynomial case in two variables. It's connected to Hilbert-16 problem, and I don't know how to get good results for this. Even kind of much weaker things than this, I'm unable to do. Yes.
Are there applications of O-minimality that you actually believe cannot be made effective, like where you actually need functions that don't live in sharp structures or effective structures?
I mean, it depends on what you want to apply. I mean, there are some theorems in O-minimality, like maybe I'll mention some point counting theorems that are true for every analytic set, for example. So, okay, I mean, it's not true, but do you have like an application from another field, like from number theory, from physics, from Hodge theory? That I'm not sure of. I mean, at least I don't know such examples where it seems to me that it's not supposed to be effective. I also don't know any case where I know that it's effective and I don't think that it should be sharp. I mean, it's kind of, it's like naturally you expect that, why would I get things that are not growing polynomial? I mean, until you find some deep reason, you can always conjecture that maybe it is sharp. Other questions?
Yes. If you go like beyond kind of analytic things like this multi-summable, is there any partial result or thought from this?
We have really, I might mention them, and we'll have a talk by Adele Paget about this multi-summable thing. So I think there it is plausible. I mean, if you have something that looks like a solution of this type of system, but now it's not analytic, it's in some more complicated, for instance, Gevrey summable class that I have not defined for you, then I think it's plausible that you can get some control, but we have not gone so deeply in that direction. Other questions? I want to mention one other kind of question or conjecture. I don't know if I should call it a question of conjecture that I thought might be a little bit interesting for the physics connection. So I mentioned that we don't have any examples of sharp O-minimality or even effective O-minimality which does not come from from differential equations. And so these are usually very rigid examples. I mean, it's really things coming from nature, some functions obeying some, these very nice algebraic differential equations. It could come from number theory or Hodge theory. But you could go in a different direction and ask, what about some generic things? Like I don't want very rigid functions. I want if I just take a generic thing, is it sharply O-minimal or is it not sharply O-minimal? Because also the counterexamples, I mentioned the counterexample with this very lacunary sequence where things grow. It seems also like a very kind of non-generic kind of example. So it's not even clear what is the usual behavior. If you just take, I don't know, some generic O-minimal structure, is it sharp or is it not sharp? So a question, conjecture. So let's F, which is sum a n z to the n, be random. Okay, random, I mean something like, pick these guys from your favorite Gaussian distribution or some. I don't want to make my question too specific, so you can nail me down and disprove my conjecture. But some kind of, take some nice, nice kind of randomness for these guys. Is R alg plus, if I just add the graph of this function f, is it effective or maybe sharp? Let's say with probability 1, or maybe with high enough probability or something. So I think this is potentially approachable. So it does not seem, I mean, if you give me a specific function like the zeta function, I really don't know where to start. If you give me a random function, then okay, it's somehow easier. So it's plausible that a random function, so if you're thinking about, I'm working with functions in nature, just I'm looking at this room and it's some just random collection of, I don't know, people and atoms, then okay, you don't expect it to satisfy a very rigid. I mean, this configuration of people does not come from number theory, but maybe you do expect it to, well, I mean, yeah, some of them come from number theory, but anyway, maybe you expect it to be kind of random in some sense, and I do expect, I wrote it as a question, but that is my expectation. I mean, I do think that if you have a random function, you have not kind of set up some special situation to get a lot of zeros, then you should have a bounded number of zeros. And that's maybe also connected to this information. You can kind of think how the entropy here is related to the degree that you would get here. I mean, how the amount of information that you have in the distribution should be related to the amount of information that you get in this function. So, but I don't have results on this. I just wanted to mention this as a nice question. And it's a question that you cannot really ask without this formalism. I mean, people have definitely looked at things like, take a function, an analytic function, and ask how many zeros would it have? I mean, this is a question that's easy to formulate and people have results on it. But I mean, here it's a much more, we are saying we are taking this function and we are building a structure. So you can now define sets in many dimensions using this function. And like, is there somehow hiding a lot of information in this function? If I wrote a complicated formula, would I suddenly get a very, very complicated set? Or is it the case that whatever the formula, I can always get a bound, an upper bound for the complexity in terms of this distribution that I started with? So it just seems like an interesting question to me. Okay, other questions? Yes.
If you expect the statement to be true, would it also hold for adding finitely many?
I mean, I would expect, yes, because you could add a function, yeah, or I mean, do it in several variables, for example. I mean, I would expect that if it's random, then it should be at least effective, and I would also expect sharp. Maybe it's easier to try to prove effective. I mean, to prove sharp, you really need to get very good control. So it's kind of natural to start by just seeing if you can get any control. I would expect both, and yeah, you can take, say, a finite number of functions and in more variables, and I still would expect this to be true.
Is it even clear that you're finding many zeros?
Well, I mean, no, sorry. So let me, they're restricted. I mean, I restrict them, yeah. So these are, yeah. So I add f on, the unit disk or something. Yeah, thank you. I brush these things under the rug. Any other questions? Yeah, I mean, certainly, if you took it on all of C, it would not have finitely many zeros unless your distribution was very strange. Okay, so now I want to talk a little bit about point counting, which is one of the main applications of O-minimality. This is, I mean, point counting is about it's theorems about counting like integer points or rational points or algebraic points in these tame structures. So, I mean, I'm not quite sure how this fits into the physics picture. So, I mean, it's like you're counting integers. Is this very relevant for physics or not? I don't know, because I don't know much physics. But I do want to show some examples where, I mean, you can use this point counting even to study problems that have nothing to do with number theory. And I mean, having this point counting result, it's kind of useful for saying something about functions that do come up in physics. So that's why I want to still introduce it. So, in point counting, as I said, we're going to be just looking at the definable set in an O-minimal structure, and we want to say something about, let's say, the rational points on the set. So I'll make some notation. So I'll take now X will be the set I'm interested in. It's in Rn. And then I'll denote by X UH. This will be the set of vectors X in X intersected Qn, such that the height of the vector is bounded by H. So let me tell you what is this height. So height of a rational number is just the maximum of the numerator and the denominator, if you write it as a reduced fraction. And if you do it for a vector, it's, say, the maximum over all the coordinates. There are many different notions of height that you can consider, but it wouldn't really matter for anything I'm saying. So if you just have a vector of numbers, you list all the numerators, all the denominators, and the maximum of these is your height. So we would be interested in kind of saying something about these sets. Okay, it's too hard to really count all the rational points in a set. This could be very complicated. We're going to do some kind of asymptotic with respect to the height. And before I can say anything non-trivial about this, I need one other notation, sorry, and that's the last one. So I'm going to denote by X alg. This is going to be the union of all connected positive dimensional semi-algebraic sets, gamma inside X. Okay, so I have this set X in Rn. It could happen to contain some curves, some algebraic curves, or surfaces or whatever. I'm going to take all of these positive dimensional algebraic things and put them into this collection X alg. And this could be a very complicated set. I mean, this set might not, I mean, even if you started with a definable set, this thing could be non-definable. Maybe it's a countable union of things, or it can be quite complicated. The reason I'm kind of pulling this aside is that I hope to say something about this, and this is simply too difficult if you're dealing with algebraic sets. Okay, so kind of understanding the integer points or rational points on an algebraic curve, it's a very complicated problem, and we are kind of, it's orthogonal to what we are going to try to achieve. So let's say even if you have a curve, understanding do you have infinitely many rational points or finitely many rational points on the curve, that's a Fields medal for Faltings. So, I mean, it's kind of, and it uses different methods not related to what I'm talking about. So I'll just pull these out and I'll call the transcendental part, this will be just everything that remains. Okay, but presumably for a lot of sets, I mean, this would be basically everything. I mean, if you took, I don't know, the graph of some transcendental function, usually there will be nothing algebraic in there. I mean, it has to be something special going on so that you would get an algebraic curve inside the transcendental set. All right, so this is the definition, and now I can state a theorem. So the first theorem I'll state is by Pila and Wilkie, which is really the theorem that started this whole direction of point counting in O-minimality. And the theorem is as follows. So now we take X, which is definable in an O-minimal structure. and I'll fix some positive epsilon. Then if you count the number of points in the transcendental part that are rational up to height h, this is going to be less than or equal to some constant that depends only on x and epsilon times h to the epsilon. Okay, so we're saying after removing the algebraic part, we cannot get a lot of rational points in a definable set. It's going subpolynomially, less than any power of h. And here, the theorem is kind of perfect. You cannot weaken any assumption. So if we didn't throw out the algebraic part, this would be wrong. You can take a curve like x is equal to y, and then certainly contains a lot of rational points. Because whenever x is rational, y is the same rational. Obviously, you'll have like h squared, roughly up to height h. Another thing is you cannot generally improve these asymptotics. So even in like the restricted analytic structure, which is a fairly small structure, you can find even curves where you get as close to this as you want. And you can find curves where, okay, it's less than h to the epsilon for each epsilon, but it's more than any function that satisfies this asymptotic. So you really can't push this down. And also it's a very general theorem. It's for every O-minimal structure, so it's quite hard to improve this theorem in any way. But there was a conjecture by Wilkie that says that you can improve it if you restrict to some special structures. Okay, so Wilkie specifically, this is from the original Pilo-Wilkie paper. He considered the structure Rx. So that's basically the structure you get where you just start with algebraic things, and you just allow yourself also the exponential function. So the exponential function is very nice. It satisfies differential equations. It's Pfaffian, so we have good control for the sets. And then the conjecture was that in here you can expect a much better result. You can expect that the number of transcendental part, number of rational points in transcendental part should be less than some polynomial in log h. Okay, so you can go from just subpolynomial to polylogarithmic. And so this conjecture was kind of the reason, the main reason for introducing sharp O-minimality. So it was kind of trying to prove this conjecture, but also trying to understand. I mean, it's clear in this conjecture that he pulled Rx out of a hat just because, okay, it's a structure that Wilkie thought a lot about. He has a very important theorem called the theorem of the complement for Rx. And it's a structure where the function is Pfaffian, so it's reasonable to expect by Chovansky that you have good bounds, even though this sharp O-minimality didn't exist when Wilkie made the conjecture. But I mean, he chose this one because he knew that it's Pfaffian, so maybe one can get better bounds in this case. And then we introduced sharp O-minimality basically to try to understand what is the collection of structures where we expect this to hold. Okay, it doesn't have to be Rx, but it should be some structure where you have good control. And I mean, the kind of good control we want is sharp O-minimality. And then in order to state a theorem related to this conjecture and sharp O-minimality, I need one more definition. I apologize, maybe the last definition of my talk. So let me make a definition. So I'm going to say that a sharp O-minima structure has sharp derivatives. If whenever you have a function f in n variables, and this function is, it's definable, it's in some omega fd, then I can tell you something about the format and degree of the derivatives. Okay, so what do I want to tell you about them? I want to tell you that for every alpha so every multi-index alpha, I can compute the derivative f to the alpha. I mean, I take, this thing is defined wherever f is smooth to order side of alpha. Let's forget about these details about where things are smooth. This is going to be in omega O f of 1. I'll explain my notation, and poly f of d and alpha. Okay, so sorry for the complicated formula. It means something simple that I will explain in words. So this I just mean some constant that depends only on the format. So I'm saying now we have a function, we are taking a derivative of some high order. I want to know, first of all, that the format of the derivative is some constant depending only on the format of the function. It does not depend on how many derivatives I took. And second of all, I want to know that the degree of this derivative is growing polynomially in the number of derivatives I took. Okay, so this is the definition that you couldn't really make in an O-minimality. The definition only makes sense because you have this filtration. Now, let me point out that, I mean, the details of what I put here are important. It is true that whenever you have a sharply O-minima structure, you can define the derivative. I mean, the derivative is defined using logical formulas, right? You can write epsilon delta definition for the derivative. So you can write a formula for the derivative, and whenever you can write a formula for something, then you can get that it has a bounded format and degree. The problem is that when you try to write a kind of a formula for a higher order derivative, you will have to include many new variables. And then this format will become dependent on the number of variables. So it will become dependent on the order of the derivative. Okay, so if you just try to do this straightforward way, you will not get this nice behavior. So when can you expect this type of nice behavior? It's when your functions are somehow related to differential equations. Okay, if I had a function that solves a differential equation and I take a higher order derivative, I can just kind of re-express this derivative again and again using my original function, right? It just becomes some polynomial combination of the original function. When I take d derivatives, I'll get some polynomial of degree d, roughly. Okay, so, I mean, so this kind of restriction you can expect when you have functions coming from some solutions of differential equations. And I don't think you can expect it. So if you just have a sharp O-minima structure that does not come from differential equations, even though I don't have such an example, but if we had such a structure, probably it would not satisfy this definition. At least I don't see why it would. Okay, so why is this helpful? So there are two facts to mention. So one is that, I mean, the case that we do know, this R-pfaf is or has sharp derivative. Okay, so this structure is generated by functions that have some differential equations, and indeed, because you have differential equations for the functions, you can show that the structure has sharp derivative. There's some work to be done, but it's not very difficult. And then we have a theorem with Dmitry Novikov and Benny Zak, who is speaking after me, which says that if the structure is sharp or minimal with sharp derivatives, then this conjecture of Wilkie holds. Then if you take x in omega fd, then the number of points in the transcendental part QH is going to be bounded by some polynomial depending only on the format of f, the format of x, in the degree of the set and in log h. Okay, and then there's the Wilkie's conjecture. Conjecture is a corollary. Not a completely trivial corollary because, I mean, the sharply O-minima structure that we have is the restricted Pfaffian function, and this Wilkie's conjecture is about the non-restricted things, but nevertheless, you can deduce this conjecture of Wilkie from this theorem. Okay, and this theorem kind of gives you a lot more control. So Wilkie was just saying that it grows polynomially in log h, but here you see that it really should grow polynomially also in the degree of the set, and which polynomial it is really only depends on the format. So it really lets you understand the growth of the this polylog growth in terms of the parameters. So I'm sorry, I remember we started late, but I don't remember how late we started. So
We started like 10 minutes late.
okay, so I should finish in 5 minutes roughly. Okay. Okay, so I want to say a little bit about why this. Okay, this point counting is important in applications to number theory, for example, because you're dealing with numbers. Okay, so so it's helpful to count numbers, and usually what happens is you have some set of numbers that you're interested in. So it could be like roots of unity, or torsion points in a Abelian variety, or CM points in a Shimura variety, and you want to say something about them. You want to count them. And the idea is that you have some transcendental map that will take these points into something that looks more like rational points. So maybe the easiest one to think about is like you know, e to the 2 pi iz. So this function is going to map the rational numbers into roots of unity. Moreover, it will transfer the height here into the order here. Okay, so if we are trying to count roots of unity in a set, we can like take the pre-image under this transcendental map and then count rational points in that set. Okay, so that is somehow, that makes it useful from the point of view of number theory. And there are many, so you can use this to prove various conjectures in number theory, like Manin-Mumford and Andre Oort, and some case of Zilber-Pink. So there are many kind of problems in number theory that you can use this idea to try to approach. So you're trying to count some interesting points, you make some transcendental change of variable, and then these interesting points become much simpler. They become rational or integers or, okay, some other, I mean, there's some versions of this that are a bit more complicated. You can replace this by another number field, or there's various things you can do here, but that's the basic idea. And I don't know if this is useful in physics or not. So maybe it is, maybe it isn't. What I wanted to mention is that there are some examples that don't really have anything to do with number theory, they do come up in physics. So the one example I wanted to write down is the Bessel function. Now, so the Bessel function J1, not just J1, but let me just write J1 of X. This is a very nice function. It has many special properties. I mean, for me, it is useful because it is kind of the Fourier transform of the unit circle. You can think of it like that. And this function is definitely not O-minimal. Okay, I mean, it's an oscillatory function. You know, I mean, the graph of it looks like this. Right? Oscillates to infinity, so it's definitely not definable in any O-minimal structure. But what you can say is that it has an expansion. J1 of X looks like e to the ix times G1 of X plus e to the minus ix times G2 of X, where these guys are definable in a certain structure called R sub G. Okay, so these are Gevrey multi-summable functions. So yeah, so this, I think this formula is basically called the Poisson-Jacobi expansion. And they basically gave an asymptotic expression for the Bessel function that, in my experience, physicists know better than mathematicians. So there's a certain, so you can write, this would be like, you know, a sum of, you know, an divided by x to the n. So it's some asymptotic thing, and this is an asymptotic thing. But in fact, these asymptotic series are not just asymptotic series, they are what are called Gevrey multi-summable functions. So they're not convergent, but they do make sense in a certain sector. And that means that you can put them in an O-minimal structure that I think Adele will tell us about in the last day. And so without going into too many details, because I'm out of time, the idea is that you have, I mean, these functions are oscillatory, but it's a very simple kind of oscillation coming from e to the ix times something that's definable. Okay, and that means that even though the function is not definable, you can like build it up of integer fibers of a definable function. Let me show a much simpler example. Let's say I want sine of x. Sine of x. It's kind of similar to this. Okay, it's oscillatory, it's not definable, but you can think about it as, let's do kind of a sine of x sine of x restricted to 0 to pi, right? So this would be a definable function. And now let's take a union of all of the translates. So let me call this set, I don't know, G restricted, right? And this would be G. So the G would be like the graph of sine, and G restricted would be the graph of the restricted sine. And now what I'm saying is that G is basically the union of, I'm going to take 2 pi n translate of this restricted G. And I'm going to go over all integer n's. Okay, so you have an oscillatory thing, but you can kind of glue it up out of these integer translates of a definable thing. And now you can try to count things about the full graph by cutting it up into these integer pieces and then counting the integers. Yeah, and in this way, we can prove various things about oscillatory functions. I will not have time to give details, but I think this is another avenue maybe to consider the connection to physics. So if you have some oscillatory phenomenon coming up in physics, often they are of this nature, just in my experience. A lot of functions like orthogonal polynomials that come up when you're doing representation theory, so spherical harmonics, these types of functions that come up in physics, they are not definable because they oscillate and the mode of oscillation grows, but they are usually kind of built up of definable pieces. And then you can still hope to use O-minimality to say something about it. Okay, so I'm out of time. Sorry for running late.
I think we have time for a few more questions, if there are any questions.
So could you say some about the main idea of the proof of the theorem?
Of this theorem.
Yeah.
So basically, the original proof, I mean, it's an idea that goes back to Hila and Bombieri, is that you are, all right, okay, let me write it in a form. Maybe what they proved, I said, is that the number of points in XQH is less than or equal to some C, depending on X and epsilon times H to the epsilon. Right, and it's been clear, I mean, even to, I'm sure it was clear to Wilkie, that what you really want to do here is to set epsilon is equal to 1 over log H. I mean, the theorem was for fixed epsilon, but the theorem is true for every epsilon, so let's try to put in epsilon is equal to 1 over log H. If you do H to the power 1 over log H, this will be just 2. Okay, so this will die. And then the whole question is, can I understand how this constant depends on epsilon? Right, if I take epsilon to be 1 over log H, how will this grow? And we hope that it will grow polynomially in 1 over epsilon. So you get a polynomial in log H. And then you can try to go over the proof and see where the dependence on epsilon comes in. And okay, it's a long, complicated proof. I cannot give really a sketch, but the idea is that you try to recover the proof and try to always keep good control about how things grow when you decrease the epsilon. And in order to get this polynomial control, you need something like sharp O-minimality, okay, and a lot of other work. But that's basically the idea why sharp O-minimality enters.
For this last part, should I think of this like more like having a symmetry? So would you say that this is possible in general, or would you? It sounds like as if it comes from the fact that your functions actually has less information because there's a symmetry, like a sine x.
So, I mean, when it's something like sine x, it's okay. It's clear that there's a symmetry, and indeed, in many of the examples from number theory, you're usually applying this kind of thing to a modular form or an abelian function, and there really is a symmetry, or maybe an equivariant symmetry under the action of some group. What was kind of surprising for us is that if you look at something like the Bessel function, you don't see a symmetry, right? I mean, it's not symmetric under translation and stuff. You have something that's really symmetric, but then you are damping it by quite a complicated thing, but it's still definable. So you have a lot of fibers. They're not the same, but somehow, indeed, the amount of information is kind of limited because this has a finite amount of information because it's definable, and this is periodic. So when you put two of them together, you get something very complicated, but there's still some remnant of the fact that you build it up from simple pieces. Yeah.
Okay, thank you. Further questions?
I have a small question. If you would take the Pfaffian closure of the Lochner-Therian with unrestricted Pfaffian closure,
Yeah.
Do you know or think it would still be effective or hope?
Yeah, I prove it's in my paper. I prove it's effective, and the proof is essentially the same proof. I mean, if you repeat,
As with same proof as.
I mean, first you show that this just log Noetherian is effective, and then you can show that whenever you have an effective structure and you take a Pfaffian closure, it's still effective. And to prove it is basically the same as to repeat the classical proof of Chovansky. I mean, Chovansky, he does it over algebraic functions, but he really just needs to know that whatever you do for algebraic functions, you have some good bounds, like Bezout. So if now instead of algebraic functions, you start with some other effective structure, you can kind of repeat the same thing. So yeah, it's in this paper. I look at the unrestricted Pfaffian closure. That's how I get exp, because exp is really important for me to get. And exp, I don't know how to get except by this way. So I'm doing a bunch of things for ln, but they're all restricted. And then I'm throwing in exp by using the Pfaffian methods. And in fact, you can do any Pfaffian, not just exp.
Okay, well then thanks a lot for the very nice lecture.